In this lecture, we are going to introduce a numerical integration technique called Romberg Integration that is applied to other numerical integration techniques to try to obtain better estimates for a definite integral. Suppose that we are estimating the integral of f over the finite interval from x equals a to x equals b. We will derive formulas for Romberg integration as it is applied to a few elementary and well-known approximation techniques when estimating this integral. The numerical integration techniques to which we will apply Romberg integration generally partition the interval from x equals a to x equals b using the partition points or nodes x sub 0, which is equal to a, which is less than x sub 1, etc., 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 all the way to x sub n, which is equal to b, so that there are n subintervals. We require the partition to be uniform so that each subinterval has length delta x, or h, which is equal to b minus a divided by n. The numerical integration techniques to which we will apply Romberg integration include the Riemann Sum-type examples of the left sum that we designate as L sub n, and that uses the left endpoint of each subinterval, and the right sum that we designate as R sub n, and that uses the right endpoint of each subinterval. Recall that these are the formulas for the left sum and the right sum. If f is twice differentiable, the global error for these formulas are both of order h. Another Riemann Sum-type formula is the Midpoint Rule, whose sum we designate as m sub n. The Midpoint Rule uses the y value at the midpoint of each subinterval for the height of the corresponding rectangle. If lowercase m sub I is the midpoint of the ith subinterval, the midpoint estimate m sub n is given by this formula. If f is sufficiently differentiable, the global error for the midpoint rule is of order h squared. The next numerical integration technique is the trapezoidal rule that uses, well, trapezoids, and whose sum we designate as t sub n and is given by this formula. One can show as an exercise that t sub n is also equal to the arithmetic mean of L sub n and R sub n. The global error for the trapezoidal rule, like that of the midpoint rule, is of order h squared. The final numerical integration technique to which we will apply Romberg integration is Simpson's 1/3, or simply Simpson's rule, that uses parabolas to approximate the integral of f. Each parabolic segment is determined over a pair of consecutive subintervals, so that n, the number of subintervals, should be an even integer. If s sub n is Simpson's ruled estimate of the integral, then s sub n is given by this equation. If f is sufficiently differentiable, the global error for Simpson's rule is of order h raised to the 4th power. To illustrate how Romberg integration works, let's first apply it to the left sum. For each number n sub I of subintervals partitioning the interval from x equals a to x equals b, the step size h sub I is equal to b minus a divided by n sub I. Let L sub n sub I be the corresponding left sum estimate for the exact value of the integral. Let E sub Li be the corresponding error when using L sub n sub I. If f is at least twice differentiable, the global error for L sub n sub I in estimating the integral is of order h sub I. This means that the global error behaves like some constant c sub L times h sub I. In general, c sub L will depend on h sub I, but should behave like a constant for small values of h sub I, or for sufficiently fine partitions of the interval from x equals a to x equals b. To apply Romberg integration, we require at least two different uniform partitions, one with n subintervals with corresponding step size h, and by choosing n to be equal to 2k, where k is a positive integer, we can choose the second partition to be with half of n, or with k subintervals. This way, we can just reuse some of the x nodes and y values from L sub n or L sub 2k, instead of starting over and computing another set of x nodes or y values for L sub k. Using n or 2k subintervals with step size h, the exact value of the integral is approximately L sub 2k plus c sub L times h. And with k subintervals and with step size 2h, since this time we are using half as many subintervals, the exact value is approximately L sub k plus C sub L times 2h. Solving this system of approximate equations for C sub L and the exact value of the integral, we get a formula for C sub L and actually an estimate of the exact value of the integral. This is Romberg integration's approximation for the integral when applied to the left sum. More precisely, this is Romberg integration's supposed improvement over the estimates L sub 2k and L sub k. Similarly, for the right sum r sub n sub I, we define the error e sub ri to be the exact value of the integral minus r sub n sub I. The error e sub ri, like e sub L sub I, is of order h sub I so that e sub ri behaves like a constant c sub r times h sub I for small values of h sub I. Using 2k for n sub 1 and k for n sub 2 with corresponding step sizes h and 2k, the system of equations for the right sum is almost an exact copy of the system of equations that we found for the left sum, giving us these formulas for c sub r and the estimate for the exact value of the integral. This is Romberg integration's improved estimate derived from the estimates r sub 2k and r sub k. For the midpoint rule, when using n sub I subintervals and the estimate m sub n sub I, we define the error quantity e sub mi to be equal to the exact value of the integral minus m sub n sub I. E sub mi is of order h sub I squared, so it should behave like some constant c sub m times h sub I squared for small values of h sub I. With n sub 1 equal to 2k and n sub 2 equal to k, we get equations for c sub m and the estimate for the exact value of the integral that are similar to the equations that we found for the left sum and the right sum. We solve these equations simultaneously and obtain these formulas for c sub m and the estimate for the exact value of the integral. This is Romberg integration's improved estimate over the midpoint rule estimates m sub 2k and m sub k. Let the error quantity for the trapezoidal rule be e sub ti, so that e sub ti equals the exact value of the integral minus the trapezoidal rule estimate t sub n sub I. E sub ti is of order h sub I squared, which is the same order as that of the midpoint rule error. So we have the exact same formula except we replace c sub m by some constant c sub t. We get similar equations for c sub t and the estimate for the exact value of the integral. So we should get almost the same set of formulas for c sub t and Romberg integration's improved estimate of the exact value of the integral. We define the error quantity e sub si for Simpson's rule to be the exact value of the integral minus the Simpson's rule estimate s sub n sub I. E sub si is of order h sub I raised to the fourth power, and so should behave like some constant c sub s times h sub I raised to the fourth power for small values of h sub I. The number of subintervals has to be even, since each parabolic segment of Simpson's rule takes two consecutive subintervals at a time. This also means that k should be even, so that 4 divides 2k, or that 4 divides n. With n sub 1 equal to 2k and n sub 2 equal to k, we get this system of approximate equations. This system of equations gives us these formulas for c sub s and the estimate for the exact value of the integral. This is Romberg integration's improvement of the Simpson's rule estimates s sub 2k and s sub k.